the last thing that we saw was from h of s on the s-plane, the pole zero pattern, in other words. By looking at the pole zero pattern, what does the magnitude response look like, and what does the angle look like? Was one of the problems, and I said that if you take a look at the Java applets on the web page, the link, there is an applet where you can insert poles and zeros, and by those poles and zeros, and by moving them with the mouse, you can design some low pass filters, band pass filters, etc. And the critical thing for that was, if you remember, as along the j omega axis, as you come nearer to a pole, the distance to the pole will become smaller. For example, for this omega value, because this is the j omega axis, and the only thing that changes or moves along this axis is the frequency, omega. So, for example, this corresponds to omega is equal to something. This corresponds to another omega, which is a higher frequency. So this is the frequency axis on the S-plane. And you change the omega values, and you take a look at h of j omega, and h of j omega magnitude is determined by the distance of your frequency, omega, to a pole and to a zero, if there is one pole and one zero. If there are more than one poles and zeros, the distances from the zeros will be in the denominator, distance from 0, 1 times different distance from 0, 2 times etc. divided by distances to the poles, to pole 1 times distance to pole 2, etc. So if the distance to a pole becomes smaller, then this magnitude of h of j omega will increase. If the distance to a zero is becoming smaller, if there is a zero somewhere near to this axis, along those frequencies, this thing will again be smaller. Okay, it will be this magnitude will be smaller. If you come near to a pole, then the denominator will be smaller, which makes the overall term to become large. So how do you design, for example, a band pass filter? How do you make it? You put a few poles here, and the conjugates of them are here. Let's say you're designing a real filter, so these both poles and zeros must appear as conjugates like this. And as your frequency comes around here, the values will be a lot, and therefore this thing, let's put a zero somewhere here, for example, and let's put another zero here, and one zero here, one zero here. So how many zeros are there? 4 zeros and 6 poles. By the way, if the number of poles is more than the number of zeros, if you go to infinity, this much frequency, if you go up a lot, the distance to zeros will be from these 4 zeros, the distance from these 4 zeros. So there will be 4 terms in the numerator, which are going to infinity. But the distances from the poles, how many of them are here? There are 6 of them. So in the denominator, there will be 6 terms, which are also going to infinity as you proceed towards omega is equal to infinity. So as omega goes to infinity, 4 of these infinities divided by 6 of these infinities, what will it be? What's the ratio? 0. It will go to 0. So if the number of poles is more, then along the frequency axis, as omega goes to infinity, the filters will go down to 0 asymptotically. And when you come close to these frequencies along this range, which is let's say somewhere here, it will be a large value. And as you go away from them towards the zero frequency, it will become smaller and smaller, and at this point, for example, it has to touch a zero because there is a zero at this frequency. Probably it will be something like this, and symmetric. So what does it look like? It looks like a, by the way, there is a zero here and here as well, so probably it will touch down to zero and then go back to zero after a bounce, probably. So it looks like a bandpass filter. If you increase the number of zeros here, it will be flatter here. So you may try that. But then you have to increase the number of poles, because at the tails, if the number of zeros is more than the number of poles, around the high frequencies, it will go upwards. We don't want that. We want to make them zero. So try these things. You should really try this applet and see what's going on. What's a good bandpass filter making strategy, for example? What's a good band reject filter making strategy? What's a good low pass filter? Where are the positions of the poles and the zeros? That's a very good thing that you have to learn. And for that applet is a good way to make practice. And for example, let's consider one filter as an example. H of t is equal to 1 over tau e to the minus t over tau, u tau. Such an exponential term obviously indicates a first order system, by the way. As the number of such exponential terms increase, it will be second order, third order, and things like that. So this will have a Laplace transform of a first order, which is 1 over s tau plus 1. And the pole here, this is the Laplace transform of that, and the pole here is at minus 1 over tau. So this thing, this example will produce a pole zero pattern like this. There's a pole at minus 1 over tau. Let's assume that tau is positive. So minus 1 over tau will be negative somewhere here. And as you see, it's a causal system, and it is right-hand sided because it is multiplied by u of t. So it extends to the right-hand side. And we know that the region of convergence for that will be to the right of the pole, like this. When is it a stable system? It's a stable system if this vertical axis, which is the j omega axis, is included in the region of convergence, and that requires tau to be 0, because then minus 1 over tau will be negative here. Only then this j omega axis will be included. And as a matter of fact, if tau is positive, then e to the minus t over tau will be a decaying exponential, which is good. Otherwise, it will be an increasing exponential, and it won't be a stable system. So the pole is there. Now, apart from this region of convergence pattern, one other question is, what is the magnitude of h of j omega, and what's the angle of h of j omega? For that, the best thing is to assume a frequency, omega, on the j omega axis. And take a look at distances from zeros divided by distances from poles. Do you see a zero here, by the way? We don't see a finite zero at this point. There is only one zero, which is at s is equal to plus or minus infinity. But the zeros and poles at infinities are out of our concern. We don't care about them. Why am I saying it is a zero? Because when s is equal to infinity, 1 over infinity will be 0. That's why it's a 0. But it's an interesting 0, and it's not in the finite range. We cannot put a 0 in a finite plane like that. So let's forget about that. We don't have a 0. So what are we going to say in terms of this magnitude then? It will be, there is no dz1 or dz2. we will put a 1 over there. So because it's 1 times this, etc. So let's assume it doesn't exist, so we put nothing, which is a simple 1. And what is this width? It depends on the point of this pole. Where is that pole? It's at -1 over tau. So what is this distance? It is 1 over tau. It's a triangle I am forming. What's the height of that triangle? The width is 1 over tau. The height is omega. Yeah, we already assumed it to be omega. So what is the distance from the pole to that point? It must be the square root of 1 over tau square plus omega square, isn't it? This is the distance that we have to consider. And well, it's not very easy to precisely draw this as a function of omega, but we may make some assumptions. And clearly this thing, the denominator is minimum, which makes this thing to be maximum at omega is equal to 0. Because if anything greater than or less than 0 is chosen, then the denominator will increase, which will make the whole term 1 over that thing to be smaller. So at omega is equal to 0, that's a critical point. What is the value at omega is equal to 0? 1 over tau square and square root. So it is tau. So for example, that's equal to tau at omega is equal to 0. But it's not a piecewise thing. That I'm just putting some legends over there. And what else can we think of? For example, at omega is equal to 1 over tau, it will be equal to tau over square root of 2 at omega is equal to 1 over tau. And things like that. And as omega increases to infinity, this thing will go down to 0. The denominator will go to infinity, and 1 over infinity will be 0. So if we just roughly try to plot this h of j omega magnitude as a function of frequency, it will start from something large and it will decrease, and the peak value will be tau, and at omega is equal to 1 over tau, for example, this will be equal to, this point will be equal to tau over square root of 2. So that's kind of a shape. It is a low pass filter, sort of. And from circuits you may remember that if the magnitude level goes down by a factor of square root of 2, if that much decrease is encountered, that corresponds to a -3 decibels point, right? That is also known as the cutoff frequency for some purposes. But we don't care about that for the time being. And I'm not interested in Bode plots. This is the true Bode plot, in other words. This is the actual plot of the filter. Bode plot is a rough approximation of this thing. And by the way, there is also the angle, because h of j omega is a complex entity. It consists of a magnitude and an angle in the polar coordinate system, and that is equal to arctangent or tangent inverse of the imaginary part divided by the real part for every pole and for every zero. For zeros, the imaginary part divided by the real part will be added. For example, in the numerator, it will be a polynomial of s, right? We have s squared plus s plus 1 and something like that. So it will have 2 zeros, for example, and we have 3 poles at the denominator. Depending on the number of poles and zeros, we just add each poles and each zeros angle. This is one of them, but there is only one pole here, so there is only one angle. What is that angle? It is the arctangent of imaginary part divided by the real part. And the imaginary part here is omega. The real part is minus 1 over tau. So the arctangent of that will give you the angle term in terms of omega. If you want to simplify it, that would correspond to minus arctangent of omega tau. This is a phase term, and if you run the applet that I'm talking about, the Java applet, the Java applet not only shows you this, which is more critical for most of our purposes, like low pass, band pass, etc., but it also plots you the angle term as well, depending on how many poles and zeros that you have. So this function, which is the magnitude, and this function, which is the angle, together will form or will give you the Fourier transform. And that is the Fourier transform determined from the Laplace transform. As I say, for the time being, we are not very much interested in the angle terms. We are more focused to this. Now, in one of the previous years, I have asked this as an exam question, because that's an S. So this is a one pole, 1 0 system. But the question is, what does absolute value or magnitude of h of j omega look like here? Let's plot the S-plane pattern. Where is the 0? The 0 is at s is equal to a here. Suppose this is a. Where is the pole? The pole is at s is equal to minus a here. This is the pole. And let's assume that it is right-hand sided, causal. Therefore, to the right of the pole will include the j omega axis and it becomes stable. No problem. But the question is, what is h of j omega in magnitude? This was the question that I asked. So you choose a frequency omega on the j omega axis. What is the distance to the 0? The distance to the 0 is this, which is, if this is omega, this is a, then that is omega square plus a square in square root. What is the distance to the pole? Again, this is a, this is omega, so the distance to the pole is again omega squared plus a squared square root. So what's the ratio of the two? 1. 1 for all frequencies. Is that good? Yeah, it's in fact very good, and there's a name to that. Can you give a name to such filters? All pass filters. This is an all pass filter, which is something very desirable. But as you see, it's not an identity system. It's an all-pass filter is different from an identity filter. An identity filter has h of s is equal to 1 or constant, which will pass everything. And impulse response is impulse. So the impulse comes in and it doesn't change. For this one, if an impulse is applied to this filter, it will change. So why is it an all-pass filter? What is the difference here? The magnitude, the magnitude doesn't change. It won't be the same as the input, but in terms of the spectral magnitudes, nothing will change. For example, let me say it like this. If your input signal is consisting of addition of two sinusoids, one of them is this sinusoid, the other one is a different frequency, a different magnitude sinusoid. So you sum them up and you get a signal. You can hear that probably. And when it passes from this all-pass filter the output will be this sinusoid, but with a different shift, a different amount of phase. Because depending on the frequency, although the magnitude will be not changing, the angle will change. Which means the phase of this thing will not be like that anymore, but it will be, I don't know, probably something like this. So what is the difference between this large sinusoid and this sinusoid? This sinusoid is, with respect to that, shifted towards right a little bit. But the magnitude didn't change. And similarly, the other one will also have a different angle as compared to the original. Shifted towards left, for example, this time, a little bit, as compared to that one. And the summation of these two, and the summation of these two will look quite different. They will have a different shape. However, for example, when you listen to that, if it's a sound that you're hearing, you will hear the same things. The sound of this and the sound of this will be the same for you, because your ears are not sensitive to the shifts. You don't care where the sinusoids are starting. You don't care about the shifts of the sinusoids. For a sinusoid, pure sinusoid, your ear will hear the same thing. Which means that your, for example, audio system is an all-pass filter which doesn't distort your signal. But it is, in fact, distorting your signal a little bit in terms of the phase only. And you're unable to hear that. All right. Now let's see some properties of the Laplace transform. Because as usual, the key to solving questions is by using the properties. The first property is linearity. As usual, this is a very usual property, and it says that if you have a combination of signals, then the Laplace transform of this combination will be equal to the Laplace transform combinations of these individual signals. This is x1 and then this is x2. So a times x1 of s plus b times x2 of s will be the Laplace transform. What does it tell you? It tells you that if you know the Laplace transform of this, and if you know the Laplace transform of that, then if you have a combined signal, you can separately determine the Laplace transform of this one, and then combine them at the output. It will help you to find the Laplace transform of complicated looking signals. You just have to decompose your signal into known signals. And those known signals will have some certain Laplace transforms, for example. And then you have to combine those Laplace transforms to determine the Laplace transform of the combination at the signal side. But the problem is, always this is a problem, what is the region of convergence of this combination? For example, the region of convergence of this one is R1. It's a region. The region of convergence of this second part is R2, another region of convergence. It's a set I'm talking about. When you combine them, what happens to the region of convergence? Let me be brief about this. I will certainly tell you one thing. You just need to check. Just first combine these things and take a look at what's happening to the region of convergence. It may be easy to say that the region of convergence is R1 intersection with R2. It makes sense, and it is correct, mostly. In most of the cases, the region of convergence of this combination is intersection of R1 and R2 regions. But in some cases, when you add them up and make necessary simplifications, you will notice that some of the zeros and some of the poles may cancel each other. And that pole which is cancelled may be critical. It may be one of the poles which is causing a region of convergence. A very important pole is the one which bounds the region of convergence. Maybe that pole is gone. Now, what can you say about that? So just forget about this intersection business. Take a look at what the new region of convergence is. And this is valid for all the properties that I will write down over there. For instance, x1 of S is a first order system like this, and the region of convergence is real part of S is greater than -1, so it is causal and stable. And the other system that we have is equal to 1 over S plus 1, S plus 2. And the region of convergence is again real part of S is greater than -1. So this one is also causal and stable. So what's the intersection? When you combine them, the new system x3 of S is equal to x1 of S plus x2 of S. So what's the region of convergence of x3 of S? What's the intersection of these two sets? It is greater than -1. That's the intersection. But what's going on when you combine them is 1 over S plus 1 plus 1 over S plus 1, S plus 2. And if you do the math, you will get 1 over S plus 2. And the region of convergence of two right-hand sided things will correspond to a right-hand sided signal, and the region of convergence is therefore real part of S is greater than -2. Really? Then this must be minus. Just check it out again. Hopefully this time it will work out. But it doesn't matter really. This -1 is just a scale. It's a negative filter, in other words. That's also possible. And the real region of convergence is still greater than -1. Real part of S greater than -1. But when you combine them, then it will be -1, and hopefully, I didn't check that, the result is 1 over S plus 2, and real part of S greater than -2 will be the current region of convergence. And it is not equal to the intersection, because the intersection is greater than -1. This one is greater than -2, which is a larger set, isn't it? It starts a bit from the left. It's a larger area that it covers. So what's happening, the thing that is happening is one of the critical poles has been eliminated in the summation somehow, in this combination, which corresponds to this combination. So you have to be careful about that. And if that is gone, the answer that you must give me will be this. It won't be, for example, I wouldn't expect a result like what is the combinations Laplace transform. You guys may come up with this solution. Okay, sir, the answer is this. This is x3 of S. And the region of convergence is this. Because you intersected these two and you said this. But before simplification, it's not possible to conclude this. So you have to be very careful. You must continue to get this, and you must tell me this. So how many points will I give if you give me this answer and this answer out of 10? What would you give to yourself? 5. All right. Then so be it. 5. Because this much is at least correct, right? Because it's not wrong. But if you simplify it, it corresponds to something very significant. So try to simplify as much as you can. 5 then, okay. Out of 10, you will get 5 if you do this. But if you give this, you won't get anything. The other 5 will be gone. Now what else do we have? The second property, it's the shift in S-plane or S-domain. If x of t has a Laplace transform of capital X of S, and the region of convergence is R, we will have a situation like this. E to the S0t times X of t, and you have to remember this property from the Fourier transform too. We'll have this Laplace transform. In the Fourier domain, it was e to the j omega 0 t. When you multiply something with e to the j omega 0 t, which is a sinusoid, it corresponds to a shifted Fourier transform. Omega will be shifted, in other words. But now we also have the real part corresponding to that. What do we mean by this? What is S minus S0, for example? Previously, let's assume that there was a pole here and there was another pole here. Let's say that this pole is R2, this pole is R1. It's just an example, and it's best to try to explain it with an example. And somehow, let's assume that the region of convergence is between the two, which is this region R. When you shift this whole thing by S0, the new pole will be where? For example, where will R2 move to? Right. It will move to, depending on S0, the magnitude of S0. Let's assume that S0 is this. This is sigma, this is j omega. So the new pole will be where? It will be at R2 plus S0. So R2 will move to R2 prime here, and R1 will also move to R1 prime here, if S0 is like that. Do you agree with this? All right. So now, what will happen to the new region of convergence? The new region, so there will be a pole here and another pole here. This is blue, by the way, it's not white. And the new region of convergence will be between these two blue boundaries. All right? So how did the region of convergence move? What is the new region of convergence? What can we say about that? How can we express it? The expression used by the book is this. The new region of convergence is the same R plus the real part of S0. Because as you see, the horizontal shift depends on this real part magnitude. If the poles are moving vertically, then it wouldn't change the region of convergence because the vertical lines will not change. So the vertical lines are changed only by the real part of this new S0. And that's how they define it. This is the definition. And what it means is more critical than how it is expressed. Whatever this expression, it's just an expression. You have to tell me that the new region of convergence starts from here and ends at here. It is moved towards right for this particular case of S0. And you have to tell me what those bounds are, depending on the problem. Okay. Another interesting property, the third one, is time scale. What happens to the time scaled signal's Laplace transform? If x of t has a Laplace transform of x of s, then what is the Laplace transform of x of a times t? It's the same as the Fourier transform, by the way. We have 1 over a times x of capital X of s over a. What was it in the Fourier domain? It was 1 over magnitude a times capital X of j omega over a. The Fourier transform was that. So it's the same thing that we have here, but when you divide S by A, the poles and the zeros are also divided by A. What I mean is this. Suppose we had an R2 here and an R1 here. Again, the same example. Okay? And this R2 determines the pole. This one also determines the pole. In between, it is the region of convergence of the original X of S, which is indicated as R, capital R. So where does this move? How does it move? Previously in the denominator there was an S minus R1, right? Now it is translated into, in the denominator, S over A minus R1, which would cause this pole. Now where is the new pole then? The new pole is at S is equal to A times R1. So if A is greater than 1, for example, this pole will go to there. If A is less than 1, this R1, this pole will move to the inside. It will be smaller or greater depending on the magnitude of A that we have. In fact, there is something very bad going on here. If A is negative, for example, minus 1, then they flip around. That's a problem. So let's forget about that problem for the time being. And let's focus to A is less than 1 or greater than 1. But in any case, the new pole is at A times R1. If A is greater than 1, for example, this will be a larger region. From here to here, R2 will be multiplied by A, and R1 will be multiplied by A. It will be a wider thing. If A is less than 1, it will be a narrower region of convergence. And the way to represent the new region of convergence is like this. They call it simply A times R. They multiply the region of convergence R by A. It may be larger or smaller. Okay, that's just the notation. But what I mean is this. The poles are at A times the old poles. All right. The fourth property is conjugation. If you have x conjugate of t, then the Laplace transform of that will be x conjugate of s conjugate. Do you remember what it was in the Fourier domain? What was the Fourier transform of x conjugate of t? It was x conjugate of minus j omega. And this is what it is. Because when you take the conjugate of s, only the j omega part will be negated. The sigma part will not change. The real part doesn't change by this conjugation. And since the real part is not affected, the region of convergence is not affected either, because the region of convergences are determined by the real parts of the poles, which doesn't change. For example, previously the pole was here. By conjugations, probably the pole will be here. The real part will not change. The imaginary part will be negated, conjugated, which will correspond to the same region of convergence. And in short, the new region of convergence is the same as the old one. It doesn't change when you conjugate your signal. Your signal, by conjugation, it's not affecting anything in terms of the region of convergence, in terms of the convergence issues. Okay. Now the fifth property is convolution in time. In other words, if you convolve x1 of t and x2 of t, what is the Laplace transform of the convolution? And as you may guess, this is one of the simplest things, just like the Fourier. It's the multiplication of x1 of s and x2 of s. Right? Just like the Fourier transform. When you convolve in time, you multiply in the Laplace domain. How about the region of convergence? I have to put a big question mark here, which is not a very big question mark. Normally, again, as usual, you must expect like the intersection of this region of convergence and this region of convergence. But it's a multiplication, and just like summation, some of the poles and zeros may cancel each other. So you have to be careful. You have to recalculate. Just look at it. If some of the critical poles are eliminated, be careful. That's it. The sixth, although it's the most important, we already know it, therefore I'm not dealing with any examples over there. The sixth one is differentiation. Now we are coming to a critical point at this instance, because this is something we are very familiar with. If you differentiate x of t in time, that corresponds to, in Laplace domain, multiplication with an s. And that is something we are very familiar with, right, from the differential equations. And even in the Fourier transform case, it was something familiar. We were just using j omega. Now we are using sigma plus j omega, which is s. Now this thing is quite nice. And the region of convergence, you must again take a look at, unfortunately. And I'm putting a question mark still, because it may be the case that x of s may have a pole at s is equal to 0. So x of s may be something divided by s times something else. That s in the denominator will be cancelled by this multiplicative s, and the pole will be different then. So be careful whether you're eliminating a pole at s is equal to 0. Okay, be careful about it. That's the only thing that we have here. And the seventh, before dealing with some examples regarding this, let's also give the dual, which is integration. That is from minus infinity to t, x of tau d tau, which is an accumulation, is just the opposite of this one, which will be 1 over s times x of s. And the region of convergence, I'm putting a question mark, because we are deliberately inserting a pole at s is equal to 0. And probably we are making something unstable, because when there is a pole at s is equal to 0, to the right hand side will not include the j omega axis. It is merely excluding the j omega axis then, which causes the filter to be unstable. However, if previously inside x of s, if there is a 0 at s is equal to 0, then that numerator s and the denominator s will cancel each other. It's possible.
But it will be an unstable cancellation.
Yeah, but it is trying to make it more unstable. But if x of s is already too stable, then that stability may cancel with this, and the result may even be stable. That's possible. Okay, that's what it is. Originally, if x of s is, for example, an all-pass system, like the example that I have erased, an all-pass system, then it becomes an unstable system. Although it was previously all-pass, now it becomes unstable. So it depends on what you previously had, okay? So these are differentiations and integrations, and these differentiations and integrations is one of the most critical things that you will encounter in terms of the exam questions too. Because from the differential or integral equations, you will translate them, transform them to linear set of equations in the S domain. For example, I will stop after this example. I'm not going to solve it, I'm just writing it. D square over dt square y of t plus 3 d by dt y of t plus 2 y of t is equal to d by dt x of t plus 3x of t. It's a differential equation, and I'm not giving the initial conditions or anything. The problem is, if it is a differential equation, we already know how to solve it in the Fourier domain, right? Every derivative is replaced by a j omega, and a second derivative will be replaced by j omega times j omega. And this will be therefore replaced by s square x of s plus 3s. Sorry, it's not x, it's y. Sorry. 3s y of s plus 2y of s is equal to s times x of s plus 3x of s. Now the questions will follow, of course. For example, what is h of s? What is the system response? The system response is y of s over x of s. Okay, that's where you will find h of s. So I'm putting a check here because you can take into parentheses and you can easily find this. And then from here, of course, the inverse Laplace transform will be necessary, and you will determine h of t. But in the determination of the inverse Laplace transform, you need the region of convergence, and the region of convergence is usually given like this. This is the differential equation of the system, and the system is causal or causal and stable. So when I say stable, it means the j omega axis is included. So you have to check out the poles and the zeros, well, poles mostly, and you have to choose the two poles which covers the j omega axis, and you say that if it is stable, then it is to the right of this pole and left of this pole, and correspondingly you will find the inverse Laplace transform. Or if I say causal, then you have to find the rightmost pole, and to the right of it will be the region of convergence. So every pole will be to the right, and take the inverse Laplace transform according to that. So at this stage you must be provided with informations like stability and causality. And I will tell you in the question, is it stable, is it causal, so you can find h of t. We will continue with these examples after 15 minutes of break. So let's give a break now.